In this lesson, we're going to cover Unit 4, Acquisition 1 on properties of covalent compounds. So first, we have to talk about what covalent compounds are. So that prefix co means shared, and valent is for valence electrons. So covalent compounds are going to have shared valence electrons. Covalent compounds are formed between groups of nonmetals that share valence electrons. There are two types of covalent compounds. So we can have something called a nonpolar covalent compound. And what makes something nonpolar is that the atoms are going to share those electrons equally. An example of a nonpolar covalent compound would be diatomic chlorine. So chlorine is a halogen. It is in group 7, so it has 7 valence electrons. If I have 2 chlorine atoms, they both have 7 valence electrons. And remember the octet rule, everything wants 8 valence electrons. So these 2 chlorine atoms can share their unpaired electron, and they can form a nonpolar covalent bond. So if we look at this, the chlorine on the left now has 8 valence electrons, 7 of its own plus the one that it shared. Same thing over here. Chlorine completes its octet by sharing 1 valence electron. These electrons are going to be shared equally between each chlorine, so we call that a nonpolar covalent bond. We can also have polar covalent compounds. And again, the difference is how they share their electrons. Polar covalent compounds share electrons unequally. An example, HCl. So again, this is a covalent compound. They are going to share electrons. By sharing the electrons, chlorine completes its octet, 7 of its own plus the 1 it shares from hydrogen. Chlorine now has 8 electrons. Remember, hydrogen is an exception. Hydrogen's happy with only 2 electrons. So again, by sharing its electron, it fills its outermost valence shell. So in this case, the electrons are not going to be shared equally. The reason that they are not shared equally is because chlorine is more electronegative. Electronegativity is the tendency to attract electrons. The more electronegative you are, the greater the attraction for electrons. So think of it kind of like tug of war. Chlorine is stronger. So while they will share these electrons, chlorine is going to pull those shared electrons closer to it because it's stronger or more electronegative. Since electrons are negative, and if they are pulled closer to chlorine, that is going to produce what we call a partial negative pole. We're going to have a greater region of negativity by chlorine. Those shared electrons are being pulled away from hydrogen, so hydrogen is going to get what we call a partial positive. We would call this a polar compound because it has 2 poles. It has a positive pole and a negative pole. One thing that is going to be important for today is when we are talking about properties for covalent compounds, it is going to depend on what we call an intermolecular force. We are going to talk about intermolecular forces later this unit, but there is going to be an attraction between a partial negative chlorine of one molecule and a partial positive hydrogen on another. So we are going to look at this attraction. The strength of this attraction will help us determine certain properties. And again, we call that an intermolecular force. More to come on that later. So now that we know a little bit about covalent compounds, let's talk about their properties. They have low melting points. The reason that they have low melting points is covalent compounds have weak attractions. Ionic compounds have high attractions, really strong attractions. There is a strong electrostatic attraction between a cation and anion, causing ionic compounds to have a really high melting point. If I had water and it was frozen and I wanted it to melt, I would have to separate those water molecules, meaning we would have to break that attraction between those water molecules. So the weaker the attraction, the easier it is to break it. The easier it is to break that attraction, the less heat energy we need, the lower the melting point will be. So in general, covalent compounds have low melting points due to their weak attractions. Comparing polar versus nonpolar, polar would be higher. Polar compounds have a higher melting point than nonpolar. They both have a low melting point, but when comparing the two, polar is going to be slightly higher than nonpolar due to the attraction between that partial positive and partial negative. So this attraction isn't as strong as something that's like ionic, where we have a cation and anion, but I still have this opposition of charge, and that is going to be a stronger attraction than if I were to have multiple molecules of chlorine. So since we have this opposition of charge, it's going to be a little bit stronger. The stronger it is, the more heat energy we need to separate those molecules. The more heat energy we need, the higher that melting point is going to be. But again, important to note that both polar and nonpolar have low melting points overall, but when comparing the two, polar would be a little bit higher. Solubility. Rule of thumb for solubility. Like dissolves like. What I mean by that. Polar solutes dissolve in polar solvents. Water is polar, so anything else that is polar would dissolve in water. Something like sucrose. Sucrose is a polar compound. It would dissolve in a polar solvent like water. Polar, polar, like dissolves like. Same thing for nonpolar. Non-polar solutes dissolve in nonpolar solvents. Oil is an example of something that is nonpolar. So only nonpolar solutes would dissolve in oil. Conductivity. Covalent compounds are poor conductors. So remember when we talked about ionic compounds, we said in order to conduct electricity, those ions needed to be free to move. Those ions, those positive and negative charges, were able to conduct. Well, in covalent compounds, I have groups of nonmetals, so I don't have any ions. Therefore, they're going to be poor conductors. Covalent compounds don't form ions. They don't have charge, so they're not conductive. Last property that we are going to talk about is, let's talk about malleability. So again, malleable is like moldable. If we were to hit it, can we flatten it or mold it into different shapes? Like metals. Metals are malleable. If we were to hit like a spherical metal with a hammer, we can flatten it. Ionic compounds are not malleable. They're going to be very brittle due to that crystalline structure. If we were to hit an ionic compound, it is going to fracture because it is very brittle. For covalent compounds, they are going to be softer or more malleable. And again, just like we said with melting point, it is due to the weak attractions holding them together. So far in this course, we've talked about properties of metals, properties of ionic compounds, and now properties of covalent compounds. We are going to do a lab where you have 4 unknowns and you need to figure out the bond type based on its property. So let's just make a little table and we'll kind of put everything together. So we'll do properties down the Y. Bond type across the top. So we have metallic, ionic, polar covalent, and nonpolar. Alright, so first property, melting point. Metals have a high melting point. There is a strong attraction between the metal cations and the delocalized electrons. Ionic compounds have a high melting point. There is a strong electrostatic attraction between the cation and anion. Covalent compounds have a low melting point. There is a weak attraction between molecules. All covalent compounds have a low melting point, but when comparing polar and nonpolar, polar is going to be a little bit higher, nonpolar would be the lowest. Conductivity. Metals are highly conductive. We can carry charge across our metallic bonds. We have our metal cations and delocalized electrons. Ionic compounds depends on the state. Ionic compounds in the solid state will have no conductivity. The reason, in order to conduct electricity, the ions need to be free to move. When we are in that crystal lattice structure, those ions are fixed in their place, so they are not able to move. When they are dissolved in water or they're melted, they're either aqueous or molten, ionic compounds are going to be good conductors of heat and electricity. So as an aqueous solution, when we dissolve that ionic compound in water, it's going to be highly conductive. Both polar and nonpolar are going to be poor conductors. We don't have any charge. If we don't have charge, we can't conduct electricity. Solubility. Metals are insoluble in water. Ionic compounds are soluble in water. Think about like salt water. Sodium chloride, table salt. It's an ionic compound. It will dissolve in water. When we get to our covalent compounds, it depends on the solvent. Polar covalent, soluble in polar solvents. Nonpolar covalent are soluble in nonpolar solvents. Like dissolves like. Polar dissolves in polar, nonpolar dissolves in nonpolar. Lastly, let's just talk about like the overall strength or malleability. Malleability or brittleness depends on the strength. Metallic bonds are strong and malleable. If we were to hit a metal with like a hammer, we can get it to flatten out. Those electrons, those delocalized electrons, are free to move among all of those metal cations, allowing it to be molded into various shapes. Ionic bonds are strong. They're going to be very hard, and they're going to be brittle due to that crystal lattice structure. If we were to apply pressure to an ionic compound, it is going to cause a shift in the arrangement of ions, causing it to fracture. Both polar and nonpolar are going to be weak. Attractions are going to be much softer and more flexible.